In this video, I'll show you how to find derivative functions for sine and cosine functions. We usually start thinking about sine as a ratio in a right triangle. Specifically, sine of theta is the ratio of the length of the side opposite theta to the length of the hypotenuse. To simplify things, we usually imagine that the triangle is embedded in a circle that has radius 1. And this makes the hypotenuse have length 1. And so, sine of theta is just equal to the length of the side of the triangle that is opposite theta. Let's shrink this down so we can add coordinate axes and make a graph of the values of sine. Now, let's add some coordinate axes. Now, the length of the side opposite the angle will be the y-coordinate of the point P. Let's increase the angle theta and graph the y values that we get. This is a graph of the function sine of theta. What would a graph of the derivative of this function look like? Let's rewind this. And now let's zoom in a bit on the unit circle. Let's think about the derivative of sine of theta. We can approximate this value by looking at the ratio of the amount of change in sine of theta per amount of change in theta for very small values of change in theta. And we should keep in mind that since the circle has radius 1, sine of theta is just the length of the side of the triangle opposite theta. Let's think about the derivative when theta equals 0. Let's look at what happens when we start increasing theta by a little amount. In particular, think about how the length of the opposite side grows in comparison to the measure of the angle. As theta increased, the length of the adjacent side, the blue line, didn't change. So, in a sense, all of theta's increase went into the opposite side of the triangle, the red line. This suggests that when theta was 0, the length of the red line increased the same amount as theta. This tells us that when theta equals 0, the derivative of sine is 1. Next, let's look at what happens when theta is close to 90 degrees, or pi over 2 radians. Since theta isn't close to 0, it's no longer the case that sine of theta is approximately the same value as theta. Now let's look at what happens to the ratio of sine of theta to theta as theta gets close to 90 degrees, or pi over 2 radians. As theta got closer to pi over 2 radians, the length of the opposite side of the triangle, the value of sine of theta, didn't really change. This tells us that the value of the derivative of sine of theta at pi over 2 radians is equal to 0. If we continue looking at how the value of sine changes as we go around the circle, we'll see that sine of pi will be negative 1, and for 3 pi over 2, the derivative will be 0. Let's zoom back out. Let's plot some of these derivative values on our coordinate axes. Next, let's think about what the values of the derivative should be between these points. It turns out that these derivative values for sine of theta all match the values for cosine of theta. So, the derivative of sine of theta is cosine of theta. Also, if you went back and examined how the length of the adjacent side of the triangle changed in relation to theta, you could compute values for the derivative of cosine of theta, and you'd find that the derivative of cosine theta is negative 1 times the sine of theta.